And we want to talk a little bit more about just why the components of forces can add the way they do. Obviously, it makes sense to do it that way, but is that really the way forces act in the real world? So let's digress for a minute and define the I and J vectors that are going to be convenient for that discussion. Okay, I is a unit vector, that is a vector of magnitude 1. 1, just 1, okay? There's no unit, no centimeters, no newtons, no nothing, just magnitude 1. In the positive x direction, so that for the I vector it's got a magnitude of 1 and it's in the positive x direction, meaning its angle with the positive x-axis is 0. Here's a picture of the I vector on a set of x and y axes. The J vector is similarly defined, but it's in the y direction. So it's a unit vector of magnitude 1 in the positive y direction. Theta in this case is 90 degrees. I don't know if you can read that 90, it's pretty badly written. But that should be obvious, knowing that the J vector is in the positive y direction, that it makes a 90 degree angle measured counterclockwise from the positive x-axis. Okay, so in coordinates in the xy system, I is the vector 1, 0. J is the vector 0, 1. All that should be obvious. Might not be completely obvious what good these vectors are, but we're going to find out in a minute. It gives us a way of talking about things that we don't otherwise have. It's a very convenient and easily understood notation. Just for an example now, what is, if I is 1, 0, what's 5i? Well, we haven't talked about scalar multiplication of vectors. I'm just going to regard it as obvious because I'm addressing a group here who's supposed to have had a considerable amount of vectors starting in any decent pre-calculus course. So we understand that 5 times the 1, 0 vector, we're just going to basically distribute this 5 through the components of the vector, and we're going to get 5, 0. And 3j is 3 times 0, 1, and that's 0, 3, the vector 0, 3. So if we add 5i and 3j, we're adding 5, 0, and 0, 3. And of course, 5 plus 0 gives us 5, 0 plus 3 gives us 3. So there's our vector 5i plus 3j in the usual notation 5, 3. Now, ultimately, we're probably going to use this notation more often than we're going to use this one. But for now, okay, let's go to the discussion of just why the vector components act the way they do. And I'm not going to be able to completely address this, but I want to make it at least plausible. We'll develop all these ideas when we start with analysis of motion and acceleration, which leads us to forces and so forth. And when we find that motion in the in any direction is independent of motion in mutually in a perpendicular direction, that's really the basis for all of this component-wise addition of forces. Nevertheless, let's go and let's talk about what all this really means. Okay, so F12, recall, your force was 8 newtons, 8.9 newtons. Okay, that corresponds to the force exerted by that first rubber band. Now, we have the x component of the force, 8 newtons down here, but I'm going to make a vector out of that component. So I'm going to say that now F12x, vector F12x, is what? It's 8.0 newtons times the I vector. So instead of just a magnitude of 8.0 newtons here, we've got now a vector. It's 8 newtons times the I vector. And here we've got F12y, and that's 8.9 newtons times the J vector. So now we can say that F12 is 8 newtons times the I vector plus 8.2 newtons, 8.9 newtons times the J vector. Now, if we're here and we're blindfolded and all we're doing is we're feeling the force, okay? We can feel the direction of the force. We can feel that we've got a force that's in this direction, and we can feel how much force there is. If we were to apply two forces, F12x and F12y, these two forces, at this point, it would feel exactly the same. So I'm going to draw a picture and discuss that just a little. Okay, if at some point we apply F12x and at the same time F12y, then their effect at that point is in every way identical to the effect of F12 at that point. Okay, so F12x and F12y vectors exerted together at a point identical to the effect of F12 at that point. Identical in every respect. We cannot make any measurement of anything at this point that would tell us whether this is the situation or whether we have just F12 acting at that point. Okay, so here we have the picture F12y, F12x, and F12 here as the result. And this picture represents the fact that F12x and F12y vectors exerted at a point are identical in effect to F12 is exactly what we mean when we say F12 equals this, okay? And of course, this is your F1x and this is your F12x and F12y. Now here we have the F13 vector from before, negative 4.3 newtons in the I direction, or in the X direction, 6.1 Newton for the Y component. And I've drawn the component vectors. F13X vector, negative 4.3 newtons times I. F13Y vector, 6.1 newtons times J, in blue here. So, in the same sense, this vector and this vector acting together at a point will have exactly the same effect as the F13 force.